In the previous video, we looked at a forced, undamped oscillation where the system was driven at a frequency that was different from the natural frequency. So omega was not equal to omega 0. You can see from when we solved this problem, if omega 0 and omega had been equal, then we would be dividing by 0 there. And so there would have been some sort of problem when we had done undetermined coefficients to find the particular solution. So let's go back and look at the case where omega equals omega 0. We're going to drive our system at the same frequency as the natural frequency of the system. In this case, when trying to find our particular solution, we need to note that the forcing term is part of the homogeneous solution. So looking back, we have A times cosine omega t, and if omega is equal to omega 0, then we have that a C1 cosine omega t, which is part of the homogeneous solution. So the forcing term is part of the homogeneous solution. So I can't guess a multiple of that forcing term because it is already in the homogeneous solution. So instead, as we did previously, we need to guess t times our forcing term. So we should guess something that's like bt sine omega 0 t plus ct cosine of omega 0 t. Now, in the interest of time, I will note that if I make this guess, and this is the proper guess, then C will end up being 0. So I'm actually going to just substitute bt sine omega 0 t. So I will need to take the first derivative here using the product rule. So that's going to be b sine omega 0 t plus omega 0 bt cosine omega 0 t. I need to then find the second derivative. I have an omega 0 b cosine of omega 0 t plus, and now using the product rule on the second term, I have omega 0 b cosine of omega 0 t, and then a minus omega 0 squared bt sine of omega 0 t. So I can combine those first two terms as 2 omega 0 b cosine of omega 0 t. And then the last term I could actually write as omega 0 squared xp, because it is just a multiple of our particular solution, xp. So xp double prime plus omega 0 xp is going to equal 2 omega 0 b cosine omega 0 t minus omega 0 squared xp, and then I will get plus omega 0 squared xp. So notice that the omega 0 squared xp both cancel. Well, that actually allows me to set this equal to a cosine omega 0 t, because that was my forcing term, and I'm going to set that equal to 2 omega 0 b cosine of omega 0 t. So b is equal to a over 2 omega 0. Okay, so then the general solution is going to be the homogeneous solution plus the particular solution. So x of t equal to c1 cosine omega 0 t plus c2 sine omega 0 t, and then plus the particular solution a over 2 omega 0 t sine omega 0 t. So our general solution is the homogeneous solution plus that particular solution. Now, just like we did before, we're interested in a little bit in the behavior of the system when it starts at rest and it has no initial velocity, so that the only thing that is driving this system is the external force. In that case, we would get that C1 and C2 would equal 0. So our solution in that case, x of t, is going to be a over 2 omega 0 t sine of omega 0 t. And so what I'd like you to see from this is that we have an oscillation at the natural frequency of the system, but this amplitude is going to grow linearly without bound. So the amplitude of the oscillations are going to continue to increase. So I've plotted this solution for you so that you can see what the solution looks like. And you have an oscillation at that natural frequency, but its amplitude increases linearly. This phenomenon is called resonance. So if you drive a system at its natural frequency, then it will undergo resonance, meaning that the oscillations will continue to increase linearly. Let's look at what this system might look like using slopes. So here I've got the system that has a omega 0 term of 2, because c is omega 0 squared, which is 4. Okay, so frequency is going to be 2. And then I'm going to drive it with a force of 4 cosine 2t. So it's being driven at that natural frequency. You can see that the oscillations are increasing linearly. If we had a mass spring system, we could push play, and you can see small oscillations start, but the amplitude of those oscillations increases linearly so that the mass is fluctuating up and down wildly. Eventually, that spring is going to break. Okay, we're going to surpass the mechanical limitations of that system because it's being driven at the resonant frequency. Now, this is the type of thing that engineers need to watch out for. There's a classic example of resonance that's shown all the time about the Tacoma Narrows Bridge, which was built in the 1940s. And that bridge collapsed due to circumstances where the wind was driving the bridge at a resonant frequency. Now, that is an oversimplified understanding of what happened, but what you should look at and realize about that system is that some sort of behavior like resonance was occurring for the Tacoma Narrows Bridge. I put some links in the video below so that you can actually see the destruction of the Tacoma Narrows Bridge as it's being driven kind of at that resonant frequency. And then I've also included a link to another video that explains a little bit more of the details and why it's not specifically resonance that occurred here, but a phenomenon that's similar to resonance.